Sorry. Hello, everyone. Today I will be talking about measuring LET in out of field. The outline of my talk will be as follows, starting with the background introduction, then reviewing a published paper, then we will conclude. Background. Despite the advantage of using high LET in heavy ion therapy, such as carbon ion, it can break up and generate secondary particle outside the primary treatment field. The fragmentations and secondary generated particles impact the overall dose distribution both inside and outside the field, because neutrons and protons and other fragmented particles exhibit different LETs along their path in Bragg peak, To do this, or to happen, there are two processes that lead these secondary particles outside the primary field. We call this the fragmentation tail. These two processes, the projectile, once the projectile collide with the nucleus and start to break up to smaller fragment and produce secondary particles. And the other way, it is when there is a high energetic nuclear reaction, causes the nucleus to shatter and produce secondary particles. These secondary particles deposit a certain amount of unwanted dose in nearby healthy tissues, contributing to unwanted biological damage, potentially increasing the risk of secondary cancer. So while the out of field produced on the fragmentation tail are typically low, they are less than 5% of the amount of total dose. However, they contain high LET, and particularly neutrons and short-range fragments. These secondary particles with high LET and short range are capable of causing double-strand break damage, which can deliver excessive amount of dose in the outfield in healthy tissues and impact the biological effectiveness in these normal tissues, because it's capable of causing serious damage, double-strand break. And because high LET radiation has a higher RBE, it increases the probability of DNA damage for these healthy tissues. RBE in carbon ion is growing with depth as the velocities of particles slow down. To make the biological dose uniform, which are calculated by RBE multiplied by the physical dose, the physical dose must be delivered non-uniformly. To make the biological dose uniform, the blue one, the physical dose must be delivered non-uniformly in order to balance the difference for the RBE, because RBE is changing with LET as well. And for us to estimate the LET, to estimate the RBE in a field mix of particles, we need to consider the distribution of LET delivered by all contributing particles including the primary beams, carbons, for instance, plus the secondary particles and the fragmented particles to determine the LET of all those particles. So we can model RPE for the out-of-field and predict the distribution of LET for each particles. Why this is very important? It is important because allow us to evaluate the secondary radiation risk by modeling RPE and optimize treatment safety by predicting LET. Also, make us sure that less risk for organs outside the target can be achieved. In addition to, we can integrate LET optimization to reduce out-of-field dose by adjusting LET distribution. This is a multi-institutional experiment was conducted to investigate the dose outside the field in particle therapies. Collaboration from Wollongong University in Australia and QST in Japan, Czech Republic and Germany's aim to characterize radiation field of secondary fragment and neutrons on the target volume by measuring the radiation field produced out of the primary field in particle therapy. Also, to assess the radiation quality and dose equivalent to normal organ located near the target volumes. This study, it's a multi-institutional studies, a very long, big study, I like. They used many active and passive detectors and Monte Carlo simulation to predict and measure the LET distribution in out of the field. Now each detectors has its own advantages and limitations, but for the sake of time and for my interest, out of my interest, I will only focus on the solid state tract detectors, specifically analyzing CR39 and FNTD out of my interest and for the sake of time. So we will start with the materials first. SR39, it's a plastic. This is the chemical name as it's shown here, figure A. It is highly sensitive to charged particles. Once the particle initiates a chemical reaction, bits will be created as the particle interact. Chemical reaction will cause this bit to be created. And those bits spot can be absorbed with an optical microscope, allowing us to identify particles in mixed heavy ion field and determine dose delivered at each bit. Different size give us different informations. CR39 is very sensitive. This sensitivity is capable of detecting specific LET values. Only particles with high LET. LET must be greater than 3.5 kV per micrometers. Any value below this cannot be absorbed by SR39. And it is very difficult in detecting and measuring short range. FNTD is short for fluorescent nuclear track detectors. It works by detecting localized damage caused by the ionization along the path of charged particle. Now, the formation of this fluorescent centers traps and cause impurity in the material. Now, by calibrating the response function, which relate to the physical quantity, such as the size of each bits or the intensity of the fluorescent tracks to the ionization loss. The LET for each track can be determined, and it offers a wide range of LET detections. Now, the method in this paper, what they did, they directed 380 MeV per micrometers carbon ions into water phantom FNTD and CR39 to measure the effect of radiation on sensitive volume, while moving the detectors further with the same dose each time irradiated to investigate a mixed radiation field. The purpose is to chapter the change in LET with increasing depth in Bragg peak. For my interest, I am only focusing on the Lecheria positions relative to the Bragg peak, the fragmentation tilt. And then they compare the result obtained experimentally with the measurement from our water phantoms. Initially, they did it with the result from the Monte Carlo simulation as well. The result. So the results show LET spectra obtained from experimental measurement and Monte Carlo simulation for the 380 carbon ions and the spread out Bragg peak at various depths. Z corresponding to each type of ions, including carbons, the one with the yellow peak here, representing the carbon. To clarify this, they measure the LET spectra from all particles at each point in the depth of Bragg peak. For example, figure A corresponds to this point in depth, which should correspond to this point on the biological dose, approximately this point. It's going to be somewhere here. Figure B correspond to this point here, which is going to be corresponding to this point in the biological dose, C and D and E and so on. And the yellow one is carbons ion. At the shallow depth from 24 to 125 millimeters, LET spectra dominated by carbon ions is the highest, more than others, and other particles and the fragments, secondary particles and fragments, they appear smaller peaks. This is this area here, ABC, the shallow depth, corresponding to this area here, the shallow depth. At the mid of the spread out Bragg peak, from 140 to 195 millimeters, carbon ion LET start to get wider due to losing energy. So carbon ions start to lose energies. So LET become wider here. And the contribution of secondary particles increase. Secondary particles contribution increasing. This area is here. DEF. DEF somewhere here. At the distal edge, from 2015 to 2021 millimeters, the contribution of secondary particles and the fragment dominates and shift to a higher LET than the carbon ions. Why? Because of range struggling and carbon ions stop. So the LET higher with the LET become higher by the secondary particle and the fragments. We're talking about the distal edge, this fall down area. Range struggling and the carbon stop. The fragmentation tails, the LET spectra, reflect only secondary particle and fragment. There is no more carbon ions. Also, at the same paper, they did the same for different particles and measure high LET above 15 kV per micrometer for different particles. The nuclear target fragmentation cross-section carbons are higher than protons, which mean carbon ions have a higher probability of causing fragmentation or causing fragments in secondary particles are more produced by carbons than protons. However, because of LET dependency of Z, the Z means the square of ions charge numbers. A fewer carbon ion are needed to deliver the same dose at sensitive volume, which means the fluence of carbon is way less than protons. The fluence was normalized for each particle to determine the absorbed dose. And the results showed that the contribution of secondary particles and fragment at the shallow depths here of Bragg peak for carbon ion is less than proton, which means low LET proton need more fluence than carbon with a high LET at the same sensitive volumes. Producing more secondary particle at this Bragg peak, the results showed that carbon 5.4 times lower for carbon than proton, and 1.6 times lower for helium than proton. On the out of field, neutrons have high penetrations, but contribute little to dose. So neutrons, they penetrate very high. However, their contribution to the physical dose is negligible. It's very little. And other ions, the number of them are less than neutrons and alpha particles, but they have high LET. However, they are very short in range for these other particles in the out of field. discussion to discuss the result. CR39 only measure high LET. Measure high LET heavy ions with excellent charge resolution and obtain statistical accuracy. It absorbs the tracks of the charged particle, and it is very difficult to detect and measure a short range. Whereas FNTD detect all charged particles. However, it is time consuming. However, it is time consuming and difficult to achieve sufficient statistical accuracy. It can determine position with high spatial resolution, can measure short range, yet its scanning speed is limited and very difficult to analyze due to the overlap of tracks with each other. The total number of secondary particles produced is lower for carbon compared to the proton at the same physical dose, according to the result we have obtained or we have analyzed. Therefore, RBE is better for carbon despite the fragmentation and the reduction of secondary particles. RBE10 decreased sharply for a depth of 146 millimeters and increased slightly for a depth of 19.41 millimeters. The amount of secondary radiation depends on the beam delivery method, with scanning beam technique generally resulting in a lower secondary particles than passive scattering delivery technique. To conclude, why it's not going to conclusion? Okay, conclusion. To conclude, CR39 plastic and FNTD are used to analyze the contribution of particle at each radiation component to LET spectra. By integrating the LET spectra for all tracks, it is possible to evaluate the absorbed dose and assess the radiation quality and predict RBE. These techniques offer the possibility of discriminating and characterizing the radiation out of the field. They are useful techniques to determine the type of particle in a complex radiation field and characterize mixed radiation field. Because of LET dependency of Z square, fewer carbon ions are needed to deliver the same dose at sensitive volume. The fluence of carbon is less than proton, which means protons will produce more secondary particles as they increase the fluence. The total number of secondary particles produced is lower for carbon compared to proton at the same physical dose. Therefore, RBE is better for carbon despite the fragmentation and the production of secondary particles. The fragmentation tail delivers an undesired dose to healthy tissues and out of field, but the low RBE mitigate harm, therefore lower biological effect. And with this, I came to an end to my talk today. I am happy to hear any of your comments or to answer any of your questions. Thank you very much. Arigatou gozaimashita.